Good evening, everybody, and welcome to the Planets and Moons chat here from the Open STEM Labs at the Open University. This is an event especially for students of S283, the Open University Planetary Science course, but we've opened it out to the wider community as well, so welcome whoever you are. We have some questions received in advance. We'll be looking for live questions via the chat window as well, and we'll answer what we can. But before we get round to the questions, we'll talk about recent events and news. With me is Martin Suttle, a new member of the S283 module team, and you'll be finding out about him very soon. We've got things to vote for in the widgets. We'd like to know where you are, and you can vote for your favourite moon, your favourite planet, and where's the best place for finding life, Mars or an icy moon. I see that at the moment it's 11-1 in favour of icy moons there, which is a surprise to some it would be, but it's only a bit of fun. Okay, well, Martin, I hardly know you because you joined us over the summer, but I know you work on micrometeorites. So yeah, give us the 5-minute lowdown on micrometeorites, because I'm sure a lot of people watching won't know much about them.
Great, yes, thank you. Yeah, I started in September, and as you say, my background is in micrometeorites. And what I mean by that is tiny grains of cosmic dust, less than 1 millimeter. So they're grains of dust in space that are liberated from asteroids and comets through asteroid-asteroid collisions or through sublimation of comets. And then that dust spirals in towards the inner solar system, and some of it is captured by Earth's gravity.
Yeah.
And then it makes a passage, a violent and flash heating passage through the Earth's atmosphere. And much of that, about 90%, burns up in the atmosphere. And we see that, we can see that in the night sky, set periods reliably as shooting stars. So the Perseids meteor shower in August and the Geminids in December.
The visible shooting stars are tiny grains. Are they actually micrometeorite size? Are they that small? I was brought up to think of them as grains of sand, but you're saying less than a millimetre.
Well, they span a bit of a range, yes. So they can be micrometeorite sized all the way up to slightly bigger, kind of, almost reaching centimetre scale.
All right.
But a lot of them burn up, and the ones that you see are the ones that burn up. But some of those survive to the Earth's surface, and of those, about 90% are fully melted, and so they pull themselves into little molten droplets, which we call cosmic spherules.
Yeah.
I study the unmelted ones mostly, and the reason behind that is because they preserve a lot more mineralogy and geology of that parent body that they came from. And in studying those, we hope to learn more about the diversity of the asteroid belt, and the different sort of water-rock interactions we can expect to see across the solar system.
Okay, so how were these things first discovered? Because they sound pretty inconspicuous.
Yeah, okay, so although we receive literally tons and tons of these things each year, they're obviously really small, so they can go unnoticed. So if we go to my first slide, we have here a picture on your screen of the HMS Challenger expedition. So there was an 1870s British expedition, an oceanographic research mission to go around the world and learn about our oceans. And they took a lot of sort of deep sea core and picking up sediments from the seafloor. And in them they found lots of these tiny little metallic spherules, which they sort of surmised might be cosmic dust.
Metallic?
Yes, quite a lot of them are metallic. So although there are metallic and silicate ones, the silicate ones actually slowly dissolve on the seafloor. So if you get micrometeorites from deep sea sediments, you're biasing yourself towards mostly the metal micrometeorites, as it were. Anyway, so in the 1890s, there was a paper published, and these were the first grains of cosmic dust recovered from the HMS Challenger expedition and realised to be micrometeorites.
And you can see on the screen, yeah?
Yes, absolutely. So this is a lovely sort of hand-painted drawing of the observations down the microscope that they saw. Yeah, so today we, as researchers, often go to Antarctica to collect our micrometeorites, and that's because the background amount of sediment that falls in Antarctica and anthropogenic pollution is much lower. And so proportionally it's easier to find micrometeorites, and they're sort of cleaner and kept in a more pristine way.
Yeah, we learned about collecting big meteorites from Antarctica in book 1 of S283, but here I didn't know until we spoke earlier tonight about collecting micrometeorites in Antarctica.
Absolutely. So there is a section in the S283 book in Chapter 9 where we talk about meteorites and meteorite collecting, and there's also a tiny hint of mention of cosmic dust in the book. So we go to Antarctica to collect this cosmic dust, and you can collect it from many different sites. So historically we melted the blue ice, the Antarctic ice, and they were doing that anyway for drinking water, but they would filter it and pull the particles out of it. But another way we can collect them is by going to the tops of nunataks, so mountains exposed above the ice sheets. And in this case, the mountain you're seeing there is Miller Butte, which is a flat-topped nunatak. So in the past, the ice sheets were higher and they kind of eroded the top of the mountain, leaving this flat surface with cracks. And cosmic dust grains actually fall sort of through the atmosphere and land either in the cracks or nearby and are blown by wind into those cracks. And those cracks have been around for at least 4 million years. We dated that surface, collecting cosmic dust. And so we scoop out the dirt from those cracks, as you can see in the pictures, and we get a whole host of amazing micrometeorites. And I've actually brought some of them to show you today. And that's what we've got on the kind of close-up camera over here. So these are actually particles embedded in epoxy resin, and we do that so that we can handle them much better, and also so that we can polish that resin once they're embedded to section the particles and see their interiors. And that allows us to study them on the SEM. So these grains are really tiny. You can see my finger here for scale, on my fingertip. And they're about 1 millimetre. And these are actually some of the largest ever micrometeorites recovered. So they're giant micrometeorites, if you will.
So what can we learn from them?
Right, yes, very good question. So actually, the way micrometeorites are transported in interplanetary space is different to that of meteorites. In the S283 book, you cover how meteorites are transported from the asteroid belt via what we call the Kirkwood gap, so specific regions in the asteroid belt. By contrast, dust grains come from everywhere in the solar system and anything that's producing dust. And the dust's angular momentum decays very quickly, and that causes dust to spiral inwards.
This is the Poynting-Robertson effect, yeah?
That's absolutely right.
We cover that.
The Poynting-Robertson effect, so something called PR drag. And that is one of the key features that makes micrometeorites a great thing to study, because they complement our perspective from meteorites and give us a better idea of the diversity of the solar system. So I sort of alluded to the idea that you could find micrometeorites in Antarctica. And a recent development in our field is the ability to find micrometeorites on rooftops and in roads and in places where we live, and the amount of kind of sediment around is full of urban pollution. And yet some very hard-working micrometeorite hunters, John Larson, Scott Peterson and Thilo Haas, for example, have demonstrated this. They've searched through literally tons of dust using special techniques like magnets to refine that, and recovered some very impressive melted particles, these rounded, shiny cosmic spherules. So I've got some here to show you in John's book, In Search of Stardust. These are photographic images, so taken under a binocular microscope, and they show the micrometeorites, which are made of silicate, with the iron-nickel metal droplets. So often during the flash heating process, they kind of begin to differentiate like tiny planets, separating the metal from the silicate. And his book is really nice because not only does he show you what micrometeorites look like through the many hard years of searching, he shows you, if we can just go back to the book again, what the false particles that you might mistake for micrometeorites are. And these, for example, are called Fuglerite spherules, so these are produced by lightning. But there are many other types, such as things produced by fireworks or welding or catalytic converters of cars. So it's an interesting field.
Yeah, so quickly, because time is getting short, what are you going to be doing here at the OU with
Right, okay, yeah. So I'm particularly attracted to the OU and to work here because of the isotopic specialities. And so there's lots of really cool kit for measuring the isotopes in these particles. And that helps us to fingerprint where they've come from, but also to study water-to-rock interactions. So the kind of early geological history of these bodies when radiogenic heating was melting ice and allowing that water to react with rock and generate muds and things like that. So that's what I'm going to be doing.
So oxygen isotope studies.
Oxygen and deuterium, hydrogen, and maybe some carbon isotopes as well.
The kind of stuff that's in Chapter 9.
Chapter 9, yes.
Coming back
the end
to Chapter 9.
That's really my bag. Yeah.
Okay.
Oh, okay. So most of our viewers are aware that you are on ESA's mission to Mercury as a scientist involved in that. And there's been some news about that recently, isn't there? So maybe you can tell us what's been going on. Yeah, sure.
Bepi Colombo, it's the European Space Agency, Japanese Space Agency joint mission to Mercury. We launched over 3 years ago now. We get into orbit about Mercury at the end of 2025, but we have a series of flybys of Mercury to help us match velocity with the planet to get into orbit. And the first flyby of Mercury was on the night of the 1st/2nd of October. So we do have some pictures back from our own spacecraft of Mercury. They're not science images because, as I'll show in a moment, we haven't got the science cameras working while we're in our cruise
Stacked
mode.
up,
But
yeah.
it's a stacked spacecraft. But we are making geological maps of Mercury, like these on the table in front of me. These are made by PhD students of mine, much bigger scale. These are just the biggest bits of paper that will fit in the photocopier, but
Sure.
or laser printer. But we're mapping the whole planet, making geological maps to show the different ages of craters, the different ages of lava flows. So that when, using data from NASA's MESSENGER mission, which orbited Mercury from 2010 to 2014, thereabouts, this will set the context for all the observations that Bepi Colombo is going to make. So I've got some pictures if we can
Let's
move
see
on to them, please.
what it
So,
captured.
and the first picture is just going to show some of these maps stuck together, just to show part of the progress towards mapping the globe. The strip from top to bottom is 3 maps made here at the Open University, and I've got a student mapping the South Polar region now, and 2 others mapping the regions to either side of the lowermost map sheet on there. So that will be 5 out of the 15 mapping quadrangles on Mercury mapped here at the Open University, and the others are being mapped in Italy and France and Germany.
What can we learn from a map like this?
Oh, well, we're looking at the distribution of lava flows of different ages, because the North Polar region, that salmon pink colour, is very young lavas, and they don't occur near anything like the same abundance near the South Pole. So there's been an asymmetry in the volcanic history of the planet. But there's still been quite young eruptions going on. We will come round to young eruptions in a little while on the Moon. But it's an exciting planet. It's volatile, rich. It's had explosive and effusive eruptions. I'm really excited that we're getting a spacecraft there. But we flew by in October. Next slide shows the geometry of the flyby. The closest to the planet there was 200 kilometres. That was on the night side. It's only when we came out beyond and we began to see the crescent shape but more of the planet, the sunlit part of the planet, came into view. Let's see some pictures from that after I've explained the cameras. This is a spacecraft. The bottom unit is the transfer module. MTM stands for Mercury Transfer Module, and there are 3 monitoring cameras, MCAM 1, 2 and 3, just schematically shown there. They were late additions to the body of the spacecraft, because the science cameras are in the second unit up, MPO, Mercury Planetary Orbiter, but they can't operate during cruise because MPO is joined to MMO, the Mercury Magnetospheric Orbiter, inside its sun shield. It's travelling as a stacked spacecraft.
Really compact.
So the instruments can't see the sky. When we get into orbit about Mercury, they will separate out, and then all instruments can operate. But during cruise, no. So we added these basically webcam things. And as you'll see, MCAM 2 and MCAM 3 had the planet in view during the flyby. So let's just look at the pictures.
So they're
nice pictures.
Tantalising glimpses of
and of course, the spacecraft, bits of the spacecraft are in the foreground. That's one of the magnetometer booms at the bottom. That's actually a view of the northern hemisphere of Mercury, and then the next shot is a view of the southern hemisphere of Mercury. I mean, you see it's a heavily cratered planet, and you can see some pressure ridges on the surface. There's so-called lobate scarps where the surface is being thrust over itself. And that's one of the antennas of the spacecraft communicating back to the ground. It's hiding rather a lot of the disk. But these aren't as good images as we'll get from orbit, and they aren't as good images we have already from MESSENGER, which was in orbit. But the final picture I've got shows one of our images at the lower left there, stitched in and superimposed on the MESSENGER view of the planet.
Oh, nice.
So you can kind of see the join between them. And because the region we saw was under particularly low sunlight, sun really low in the sky, it's really brought out that escarpment.
The
topography shows it really nicely. So we've got a healthy spacecraft on its way to a good planet. We're flying past again in June, and we've got a total of 6 flybys before we get into orbit. So the flybys will keep us excited for.
So I mean, it was the best possible news you could have expected, I guess.
Absolutely, yeah. We will get round to your questions soon. Nobody's asked a live question yet, so please do use the chat for asking live questions. But we'll ask some questions we've already had on the S283 forums first. But first of all, we'll just talk a little bit about what's in the news. Now, Martin, what's caught your attention in the science news lately?
Great. Okay, so in my field, I've been keenly observing the discovery of this new andesitic achondrite. So what that means is it's a fragment of a crust of a former protoplanet that no longer exists, And it's quite unusual, incredibly unusual. There's maybe only a handful of andesitic meteorites. So that's to give some context. An andesite is sort of a rock with an intermediate composition between a basalt and a granite. So we're familiar with all that range of rocks on Earth, and of course the andesites are named after rocks we find in the Andes on Earth. But it's actually a more silica-rich rock than a basalt, so it's got more silicon dioxide and less iron and magnesium. Yeah. And to generate such a composition, you need maybe a high degree of partial melting or a complex crustal process. So on Earth, we generate, or Earth's crust generates such a composition by a progressive series of partial melts, and we term that an evolved composition. And that's actually different from how we think the andesite formed on this particular protoplanet. So if we just go to the slides I prepared,
you're going to show us a spidergram, aren't you?
I am indeed, yeah. We can see just a quick screen grab of the front of the paper that's come out, and then on the right is this spider diagram that we're talking about, and we have a slightly enlarged view of that. So the spider diagram plots the abundance of elements relative to something, and it's usually a carbonaceous chondrite, and in this case it's a CI chondrite. And that's very typical. And the type of elements you're seeing here are the trace elements, so they occur at very low abundances, and they're rare earth elements. And the sample of the rock we're talking about is shown by those stars, and you can see it's basically flat, which means it's got a chondritic composition, and we can relate that composition quite confidently back to a non-carbonaceous chondrite. So something like the ordinary chondrites or the enstatite chondrites.
But it's about 6 times enriched in
Six
rare
times
earths
enriched,
compared
yes.
to chondrites?
So I'll come on to that in a moment. But that flat profile means that it's had quite a different formation history to perhaps the type of andesitic rocks that we would find on Earth, which often have anomalies, so depletions or enrichments as a result of that partial melting process. And so what we think happened here with this particular protoplanetary andesite is that the planet experienced a very high degree of partial melting, perhaps as high as 25%, and that partial melting meant that all the trace elements that occur in very unusual small minerals, like the phosphates, for example, completely melted and moved into the melt phase. So there was no fractionation of these trace elements that we're used to seeing on things like Earth. And so this attests to the idea of a planet which had a very high initial thermal budget, probably driven by the radioactive decay of aluminium-26, and that was able to melt more rock when it generated this crust.
Yeah. Okay.
So it's pretty exciting. And then one final thing I want to highlight is it's the oldest igneous rock known. So it's formed about 100,000 years after the formation of CAI. So it's formed very fast after
was it
the formation of the solar system.
4.56 billion years old?
Exactly.
Yeah, that is pretty old.
Cool. And I think you brought a news story as well to do with younger things.
My story is about young igneous rocks. It's about the young age of some lunar basalts in the samples brought back to Earth by Chang'e 5. That's a Chinese lunar lander, which landed on the moon in December last year. In fact, took off from the moon again in December last year and brought some regolith samples back. About 3 kilograms, I think. It's quite sizable.
Quite a lot of material.
More than we ever got from the Soviet landers. But anyway, the age has just been published. Let's just have a quick look. This is the isochron. It's a lead-lead isochron. It's not an isotope system that we deal with in S283. But the important thing there is the age, 2.03 billion years.
2 billion years old, basically.
Whereas you'll read on page 78 of Introduction to the Solar System, our book, the lunar Maria complies basaltic flows dated at 3.8 to 3.2 billion years.
Much younger.
This is well over 1 billion years younger than those. You might think this is a surprise, but it wasn't, and I'll show you why. So if we go on to the next picture, this is just a view of the lander. So it was a fairly level, safe place to land, and I just scooped up some of this dirt.
Just to say, this is a fisheye lens, which is what you're seeing the distortion. That's not the curvature of the planet or anything.
That's right.
Just gives you some context of where the sample was taken.
Absolutely, yeah. Thanks, Martin. So let's see the wider context of where the sample came from. Okay, this is the northwest or upper left-hand corner of the moon if you're looking from Earth's northern hemisphere. That's Oceanus Procellarum in the centre. If we just advance one slide, that will add a star where Chang'e 5 landed. So it's in that region there, just leading into Mare Frigoris. And that was chosen because crater counting the density of superimposed craters which you can do from Earth or from orbital images. Well, orbital
Whenever
images.
you get images of a surface of a planet, a good resolution.
Yeah, it's not based on Earth-based images. You don't see enough craters, but from lunar orbits or orbital pictures, crater counting can be done. You learn about crater counting in chapter 3 or 4.
One of the terrestrial.
So crater
chapters.
counting works. Let me show you. Here's next slide is coloured in. It's a Mercator projection with the ages of the lunar Maria colour coded with age. And if you can read the colour scale at the bottom, on the right-hand side is 4 billion years, the left-hand side is 1 billion years. And so the warmer-looking colours are younger. Well, where was the landing site? Next slide, we'll have the superimposed star.
Oh, there it is.
It landed there in amongst the sort of 2 to 1 billion year old surface. And lo and behold, the sample that came back was 2 billion years old. So it's a wonderful vindication that crater counting is somewhat reliable.
Just to get this right, we estimated the age of the surface of the moon based on the number of craters. We went there and collected a sample, brought it back and radiometrically dated it. It was pretty much exactly what we expected.
Yeah, pretty much, except that we expect the age to vary on a smaller scale than than is resolved in this colour variation. It's quite a coarse map. But anyway, it's well within the range of what we expected. So it works, which is really nice.
Yes, that's good news for
well done,
crater
Changa
counting.
5, and well done our colleagues at Manchester University who played a big role in teasing out this lead age.
It's a difficult thing to do, isochrons.
Yeah. Okay, so we're going to go on to some questions now. Okay, well, the first question we've had in advance is from S283 student John Mayle, and this is one for you, really, Martin. He says, if a small meteorite lands in my back garden, do I own it? What should I do to preserve it? And if I want to donate it to scientists, who should I contact?
Right, well, that's a really good question. And it's a particularly timely question because, as some of you maybe know, we've had a recent major meteorite fall and recovery in the UK. So on the 28th of February, the last day of February this year, the Winchcombe meteor fell. So this was seen by literally hundreds of doorbell cameras and CCTV cameras, as well as 6 of the UK's Fireball network cameras, camera networks. So these are cameras we have on rooftops dedicated solely to looking for meteors. And it landed, actually, the main mass landed on the driveway of a family. And so under UK law, if a meteorite lands on your property, it is indeed yours. And so this was the property of the people whose driveway it landed on. They ultimately elected to donate it to science and to pass it over to the Natural History Museum collection, which is the kind of UK body responsible for looking after Britain's collection of important and geologically interesting rocks, including space rocks. And so what we would really very strongly encourage you to do is to document as best you can the full site, so photograph it in situ without touching it to begin with. Don't put any magnets near it. Wear plastic gloves and put it into a clean plastic container that's ideally airtight. And this is all to preserve the pristine organics that are present in these meteorites, the magnetic signatures that are present in meteorites, and also a lot of these bodies are incredibly reactive to Earth's atmosphere. So they spent most of their time in the kind of vacuum of space or in the reducing conditions of our parent body. And Earth's oxygen-rich and water-rich atmosphere rapidly reacts with them. And so that's the first port of call, and then you can sort of send some in or contact the Natural History Museum. And that doesn't mean that you're donating it to them. They'll just take a first pass and give you an idea of whether it's a bona fide extraterrestrial rock.
I was busy answering about that Nature paper, so I didn't notice. Did you actually say who owns it if it lands on your
I did, yeah. So the property owner, not the finder. So if you find it on someone else's land, you don't own it. The property owner will own the meteorite. Yeah.
But it's excellent that the bulk of Winchcombe was donated to science.
Absolutely, yeah. So the Wilcock family very generously donated the main mass that landed on their driveway. That was about 300 grams. We found another 150-gram stone through a dedicated search through a variety of UK planetary science institutions going out and hunting for it. And then about 4 other smaller masses, about 20 grams, were found by private individuals on their land, including, I think, one was a solar farm. So.
It wouldn't make a nice specimen to keep on your mantelpiece anyway, because it's going to fall apart quite quickly over time, isn't it? Being very friable.
You have to curate these things, so they really, as I've stressed, like to be in no atmosphere at all, or at least an inert atmosphere. And it's, in particular with winchcombe, it's very black and powdery, so it's not quite as impressive visually as a palisite or something, but it is incredibly important for science.
Yeah, absolutely. Thanks for that question, John.
Yeah, of course. So. Vic Hughes asks about the free oxygen and the discovery of free oxygen in the atmosphere of Io, which is the innermost moon of Jupiter, and whether the presence of this free oxygen is any indication that there could be life on Io. So maybe you could answer that one for us, Dave.
Yeah, thanks for the question, Vic. You don't say where you got this news of the discovery of free oxygen on Io. I don't think it's anything new. And also, what we have on Io is mostly just not O2, but O. Just single atoms of oxygen, so it's nothing that would be breathable by animals.
So a highly reactive species.
Highly reactive, yeah. And the atmosphere of Io is incredibly tenuous. It's denser than the Moon's atmosphere, but nowhere near as dense as Mars' atmosphere. It's a volcanically produced atmosphere, and where the oxygen or oxygen atoms come from is by breakdown of sulfur dioxide. It's photolytic decomposition. Solar photons, especially ultraviolet, will hit the SO2 molecules and break them apart.
Rip them apart.
Now, there was a paper from 2002. Well, let's see Io first of all. Next slide, please. I've got a view of Io sunlit, and you can see a volcanic eruption plume on the limb at the left.
It's such an odd body.
It's marvellous. It's the most foul-tasting pizza you could possibly eat because it's covered in sulphurous products. The view on the right is Io seen in eclipse in Jupiter's shadow in visible light. It's a long exposure really from Galileo. This is basically an auroral glow through the whole of the atmosphere. I suspect the bright spots are eruption plumes, but it's got this very tenuous exosphere. None of it's bound to the surface. But that's being, when it's in daylight rather than in shadow here, it's being attacked by solar photons and broken apart. Next slide is a paragraph from the paper, I think. Okay, here's the paper. Yeah. So if Fiona McGibbon wants to look up this paper, here's a reference for you, Icarus, volume 56, 2002, Photochemistry of a volcanically driven atmosphere on Io. So it talks about breakdown of SO2 to atomic and molecular emissions from these neutral species have been found. O, S, sodium, chlorine, hydrogen, SO2, and SO. So there's been the richness of Io's diffuse atmosphere has been known for a long time. And the final slide from the paper is one of the tables in the paper. And look at the production of O in the top line. It's breakdown of SO2 plus a photon, that's what the H nu means, goes to SO, that's sulfur monoxide plus O. That's where your O is produced. That's the bulk of the free oxygen surrounding Io. It's photolytic destruction of SO2 molecules, also known as photolysis. And you learn about photolysis in the terrestrial atmospheres chapter of the introduction of the solar system book, yeah. And you learn more about it in terms of what happens photolytically in Titan's atmosphere in the astrobiology book as well. So you've touched on a process, Vic, which you'll learn more about in S283. I think this is the time when we said we'd look for some
it is indeed.
live
I'm
questions.
Just seeing if you've posted any.
Well, yeah, I flagged a couple there. Well, Stephen White is asking, can the actions of the Russians yesterday concerning the ASAT test be construed as anything other than reckless? Some of you will have seen the news that the Russians used an anti-satellite missile on one of their own satellites, blasted it to smithereens, so it worked. But they created a cloud of debris in low Earth orbit. The crew of the International Space Station had to go into their lifeboats as a precaution, 2 of them being Russians.
It's been covering the news quite a lot today.
A lot of people are very upset about this reckless action.
I suspect it was a demonstration of capabilities and perhaps a sort of trial to see what how the debris field would change. I know that at the Natural History Museum, where I used to work, we have a long history of studying these kind of impact debris. So We used to get material from various satellites that have been in space and take a look at the impact craters, these tiny impact craters produced by debris or micrometeorites, on the surfaces of these objects and study sort of how we could better improve our defences against things like that.
Yeah. Is it the film Gravity where
it is indeed,
the
yeah.
disaster that happens is one satellite breaks up another one that creates a debris swarm which then escalates?
That's
So
right,
that's the catastrophic scenario that the actions yesterday could have led towards. Now, will we go to John McCluskey's question, do you think?
Yes, I'd be. Yes, let's have a look at that. So John McCluskey asks about the difference between Saturn's and Jupiter's moon. So Jupiter has 4 very big moons, the Galilean moons, relatively close in, and then after that, not very much. Whereas Saturn has perhaps a more even distribution of moons of various sizes. So, have we any thoughts on why that's so different and how that might have originated?
Well, the way you put it, Martin, it does sound different, but both Jupiter, Saturn, and Uranus have pretty much the same basic geography of their moon systems because they've got inner moons which are prograde small objects. Io isn't the innermost moon of Jupiter. There's some smaller ones inside it.
I did know that. Yeah.
So you've got inner moonlets orbiting prograde. Then you've got your regular satellites,
the big ones, yeah.
the Galilean moons at Jupiter, or Titan, the only big one at Saturn, plus Enceladus and Mimas and Dione and Rhea and so on.
Indeed.
And you've got a similar family at Uranus. And then beyond those, you've got irregular moons. Some of which are prograde, especially the inner ones, and most of the outer ones tend to be retrograde.
Perhaps we should just remind the prograde-retrograde distinction.
So prograde is going around the planet in the same direction, but the planet rotates, and retrograde is going in the opposite direction. And most of these moons are pretty close to the planet's equatorial plane, except for the outer moonlets, which can be inclined at 20 degrees or something.
So I see you're edging towards 2 distinctions, a sort of prograde, relatively large size formed near the equator, and the retrograde, maybe irregularly shaped further out moons.
Well, irregularly shaped because they're small. You have to be more, if you're icy, you have to be more than about 200 kilometres in diameter to have the mass to pull yourself into a spherical shape. No, my distinction are inner moonlets, prograde, regular satellites, then the outer ones, some of which are prograde, some of which are retrograde. But they all may be captured objects.
Mm-hmm. Indeed.
But why Jupiter has 4 big ones and Saturn only 1? Who knows? But if you look at planetary systems around other stars, they're not all like the solar system, far from it. There's a lot of variety. So I don't think we should expect all moon systems to be the same.
Is it possible that maybe Saturn had perhaps one larger moon that was smashed apart and some of these smaller moons we're seeing are fragments of that? Is that a solution?
It's possible, but I think you could probably grow Saturn's regular satellites in situ in a sort of circum-Saturn disk as well, rather like planets possibly grew around the Sun. We don't really know, but there are some ideas that some of Saturn's moons might be quite young and they don't go back 4.5 billion years. So it's an open playing field, really.
Sure.
But I would be surprised if Saturn did have 4 large moons and Jupiter 4 large moons.
Perhaps not as extreme, as that.
So I'm not. I don't think when you think deeply about it that it shouldn't be a surprise that we see this much variety. But how to explain it in detail, we just don't know.
And it's a very interesting question.
I've got one. Let's see if we've got a live one. Okay.
2 more.
Oh, all right. Clive Werrett. Here you go. Continuing the reckless theme, could DART go wrong? Is DART a mission to divert an asteroid?
That's right. It's called the Double Asteroid Redirection Test.
And
so this is something to be aware of because it's going to be active sort of in the news next year when the main phase of the mission occurs. It's not a mission I know loads about, but the idea is to test if we can sort of kind of planetary protection idea. So test if we identified an asteroid that might hit the Earth and we could redirect that. And so they've chosen this binary asteroid, so it's one large asteroid with a relatively small moon. And to avoid
Didymos, yeah?
Didymos.
And they're calling the very small moon Didymoon. They are. Did you not know that?
I knew the names were something like that. Yeah. So to exactly avoid the situation where they might nudge this perfectly safe asteroid and it turn into a collision with Earth, they're actually nudging the moon of the asteroid rather than the asteroid itself.
Yeah.
And then we're going to subsequently review that with a later space mission, I think called Hera, sort of 4 or 5 years later.
Clive's saying, could it go wrong? Could we push an asteroid into an Earth collision orbit?
So I believe, as I understand it, the chances are less than 1 in 1,000. So probably not.
Yeah, okay. I won't lose sleep over it.
No, you shouldn't. Yeah, and that is, of course, the theme of another film. I think it's Armageddon, is it? Where they try and... There's
There's
some
a
sort
comet
of film.
coming in, isn't it, Armageddon? Somebody can tell us in the chat whether... Here's one for me. Joel Weatherly. What sort of resolution will Bepi Colombo be able to map Mercury? Would we see any slight changes of Mercury, such as a new crater in the time between Messenger and Bepi Colombo? Good questions, Joel. The highest resolution camera will be better than 5 meters resolution, and we'll get about 20% of the globe mapped at that resolution. There is one new crater on Mercury, which is where Bepi Colombo crashed. Where
Surely
Messenger
not.
crashed.
Absolutely.
We don't know exactly where. We've got a rough idea where it is, but we don't have a high-resolution picture of that spot before Messenger crashed to compare with the after picture, which we will get.
What will that tell us about either the surface of Mercury or improvements?
If we know we've got somewhere that was exposed, the ejector was brought to the surface only 10 years previously, we'll be able to measure the rate of space weathering, because surfaces do change colour with age. The solar ultraviolet causes various mineralogic changes. Surfaces darken and redden with age. So we'd really like something that's been very freshly exposed. But the crater from Messenger's only going to produce debris extending for about 20 metres. It'll be a small, bright spot.
Sure.
And we won't be able to prove that this is the new spot. We're mapping Mercury in X-rays to give the elemental abundances at a spatial resolution of 10 or tens of kilometres, depends on the elements. That's the British contribution mix, the Mercury Imaging X-ray spectrometer. And there's a thermal infrared imaging system, led from Germany, which will give a lot of mineralogical information at some hundreds of metre scale. So we're going to have a lot of very good compositional data.
What's my question for you, if I'm allowed to ask one, would be what's the big science question Bepi Colombo is going to try and tackle for Mercury?
Well, there are many. I mean, why does it have, a magnetic field when Venus doesn't? Well, its outer core must be liquid. But why has it got an enormous core and a very thin rocky carapace? Was it involved in the collision to strip away much of its original rock? But if so, how come the rock that is there is rich in volatiles? Because there's 2 to 4% sulfur wherever you look. There have been explosive volcanic eruptions. They can only happen if the magma is rich in gas when it reaches the surface. So you don't expect volcanic gases, you don't expect lots of sulfur. And parts of the surface are sort of dissipating away to space. There's a phenomenon called hollow formation, where the top 10 or 20 metres has gone. And you've got steep-sided, flat-bottom depressions where 10 or 20 metres has gone away to space.
Do you think there maybe that's the presence of some sort of volatiles in the subsurface?
Lots of volatiles, yeah.
Heated up?
Well, not in the subsurface, in the surface, because it's just gone straight to space. You don't see anything collapsing into underground caverns. It looks like the surface has been stripped away.
Right, okay.
It's weird, and how do you do that unless 100% of the surface material is volatile? How are you removing 10 metres of it?
I guess
it's a mystery. It's a big puzzle. There's a lot about Mercury that we don't understand.
I'm sure there is. I didn't mean to suggest there wouldn't be. I just wanted to know what your
here's
top
one
question
for you
might be.
From Ben. Have there been any attempts to capture micrometeorites from orbit and bring them to Earth for study? And would there be any advantages to that?
Sort of yes and no. So they use
aerogel.
Yes. There was something called the Long Duration Exposure Facility where we popped up, I can't remember what year, maybe 98. We popped up a large sort of metal sheet, basically, set as a series of grids, up in high Earth orbit, and just exposed it to get hit by space debris and micrometeorites. And that would allow us to understand both sort of how we can better protect objects from collisions with cosmic dust and space debris, and also the flux of that, so how much of this dust are we receiving. And that's largely where that 40,000 tonnes per year estimate comes from. But as you alluded to, there's another way we can do that, because that surface was a hard surface, so they slam into it and they completely are destroyed and form impact craters, tiny impact craters. The alternative is to use something that was sort of generated for the Stardust mission, where in 2006 NASA flew a spacecraft through the coma of a comet, Vial 2, and that was a super low density material. I believe it's the lowest density material ever generated by humans, and it's also almost pure silica, and so it's compositionally very pure. And that's designed to slow material down very efficiently without sort of heating it up, and so as to preserve the particle you're trying to capture. So we could do that. We don't currently do that, or at least I'm not aware of anything like that. The only thing I can say that's slightly similar is sort of in the 80s and 90s, NASA flew these very high altitude planes in the stratosphere with sort of sticky silicone on the wings, and that captures tiny grains of cosmic dust in the silicone.
Yeah, I'd heard about that. There's a question in the Moon's Facebook group from Matthias Wolf. He says, a very long time ago, I read the solar system has only one moon, which is the name of the Earth's satellite. Nowadays, the word moon seems to be the accepted term for anything going around anything. So is it strictly still the case that moon with a capital M denotes only our moon? And is this official?
Oof, I'm not so hot on the official terminology, but yes, I believe that's correct. So the moon with a capital M is of course our moon, the moon of Earth. Whereas
it's its name.
Indeed. Whereas we do refer to, in the vernacular, the natural satellites around other bodies as moons.
Yeah, and you shouldn't be too Anglo-centric in your thinking, because in France it's La Lune is our moon and Les Lunes de Jupiter are the moons of Jupiter, and it's the same in Spanish and Italian as well. They tend to make the same distinction. I don't know what to do in German, where all nouns take capital letters.
Interesting.
But in English, most people will, if they're careful, will when they write moon with capital M, they mean our moon. But when I write for one particular online publisher, their house style insists that moon must always have a lowercase m, and that is very confusing when you want to compare our moon with Jupiter's moon, called Io or something. But it's a mess. I think it helps clarity to use capital M for our moon, but it isn't official, Matthias. It's not an official decision. Sensible people will do that, but not everybody.
So we have a question from Alexander Webster, who asks that when samples are returned from Mars, so that's another high-profile mission, the Mars sample return, will radiometric dating be carried out, and is there any expectation that the Mare normalized surface dates may be incorrect? So,
they will be radiometrically dated, won't they?
That's definitely
part of the point. They'll also be analysed for biomarkers.
In pretty much every way we can. So whenever we get a sample returned back, we try and squeeze out as much information as possible from the often tiny amount of material we have. Yeah. So,
dating the surface of Mars by crater counting is currently much the best way we have, the only numerical way, really.
From remote sensing, of course.
From remote sensing. And we have to try and carry the lunar cratering timescale to Mars and allow for it being further from the sun, so you've got a slower arrival speed of your cosmic debris, and it's more spread out, so there's less of it. But it falls on a planet with bigger gravity, so the crater sizes are a little bit different there. And then Mars is active geologically. You've got erosion going on and transport and burial. So dating the surface by crater counting on Mars is fraught with many more difficulties than you'd get on the Moon or Mercury.
And we have no anchor points to date.
No anchor point. No, quite.
Yeah,
which is I think
the whole
the point here. That once we've got an anchor point, we've got a sample that we know the age of. Will that refine our timescale? It possibly will. I don't suppose it will be a radical difference.
So for those that are not familiar, the Mars sample return sort of it's a sort of mega mission because it's composed of multiple missions. NASA's Perseverance rover at the moment is going out and collecting lots of material from sort of not that distant sites, but multiple different sites. And then there are at least 2 or 3 other missions that are involved in how we get those samples back. And that's a collaboration between NASA and ESA. And there's a whole bunch of planetary protection principles, which is a concept that's covered in the astrobiology textbook, to do with that, because we're bringing samples back from Mars to Earth, and we don't want there to be any contamination, ideally, in either direction.
Yeah. We've had a contribution from Germany. Pascal Brusselbach, hi Pascal, says that in being a German speaker, he'd use the indefinite article for other moons and the definite article for when referring to our moon.
Oh, that's really nice to get
So
the clarification.
Das
So thank you.
Mond or Ein Mond. Is it Mond is moon in German, I think? Pascal can put us right in the chat. So difference between articles, even when you haven't got capital letters to play with. We're getting a bit short on time there. Tom Widdowson has just popped up. What are some of the key findings that could come from another mission to the outer solar system?
I would love more missions to the outer solar system, and indeed that was one of the questions I wanted to put maybe as one of our widgets. So the outer solar system is a much harder place to explore. It takes longer to get there, of course. There's less energy from the sun, so solar panels are considerably less effective. But we can learn so much more about our solar system by exploring the outer regions, and that's perhaps been realised with things like NASA's Dragonfly mission to Titan. We can learn about differences in the kind of cosmochemical gradients as we travel out from the sun. So multiple different volatile snow lines, as it were, are expected to have existed in the outer solar system. And the condensation of those volatile species like ammonia, carbon monoxide and nitrogen can make real big fundamental changes to the mineralogy and geology of the objects that form and also their later evolution. And you can see that in things like the icy moons, where they have water, ice to rock ratios that are completely bizarre for what we see in the inner solar system, for example.
As a geologist, I would love to see Triton, Neptune's big moon, in the same detail that we saw Pluto from New Horizons.
Yeah, because Triton is supposed to be a captured Kuiper Belt object, so in turn that's allowing us to learn about a reservoir of primitive bodies that exists sort of beyond Neptune that are very icy as well.
It was quite likely that Triton had a lot of tidal heating when it was being captured into orbit about Neptune, so it might not be very primitive now. But geologically, the things that have gone on there, we don't understand the Cantaloupe terrain. And I'd love to see the unseen 70%, basically, of the moons of Uranus. What's Miranda's backside like, or what's Ariel's backside?
Because of course they were only ever imaged by Voyager 2.
Voyager 2, and we only saw the polar regions because of the actual inclination of Uranus. So there's so much waiting for us out there.
Uranus and Neptune are very, very poorly studied in comparison to the rest of our solar system.
Okay, time is getting very short. Shall we do John Mayall's question? But before we do that, let's just look at the widgets. What's your favourite moon? Fairly evenly split. Ganymede was your favourite.
Ganymede was my favourite, and it's despite being the biggest.
it was difficult producing that list. So Europa has won, the Moon and Io tying for second place. And what's your favourite planet, excluding the Earth? And Mercury's lost. Oh no. It's probably only me that voted for it.
Look at that nice correlation as you go out from the solar system.
Mars is picking up some votes, but Saturn, the clear winner there. Well, it's got lovely rings.
Yes, how many of you voted because of the rings?
Yeah. And which setting offers a better chance for finding life? 22 for icy moons, only 4 for Mars.
Wow. The audience has spoken then. They think our best chance is in the outer solar system.
Well, you can fly through the plume of Enceladus and sample it. On Mars, you have to land, but you're only going to find life on Enceladus. And dig in the dirt. Yeah, you only find life on Enceladus if it does exist there, but at least getting a sample of it is easier.
I would tend to agree. So I did vote for the icy moons, and I'm very excited for the sort of research to come on the icy moons because they're so poorly studied and yet have so much potential.
Andrew Grant, where can we get Moon Trumps cards from? These are Moon Trumps cards. You can get them from the OU Students Association online shop. I was looking the other day. My PhD students are playing with these in their tea breaks now. I think they're £7 from the USA, OU Students Association shop. So good stocking fillers, and the proceeds go to USA. Guy Watkins is asking about Planet 9 based on the old IRAS data.
So discovery of another distant planet based.
Yeah. I haven't looked into it deeply, have you? What I've seen on Twitter suggests don't get too excited, folks.
Yeah, so I think neither of us are as well informed as you are, Guy, about this particular aspect. But it would have to, of course, be a very distant object, and therefore is probably quite small. It's not probably going to fit the trend as we've seen, with the gas giants turning to ice giants. I don't know.
But if it's in the Kuiper Belt, it can't be a planet because it won't have cleared its orbit of things of comparable size.
Unless there's, yes, I completely agree. But unless there's more structure to the Kuiper Belt than we realise. I don't know, for example, a band that's been cleared.
It might have cleared, but there's no signs of a cleared
Indeed,
band.
yeah, this is all very, very speculative.
It depends if you believe the definition of planet. But even so, it could be a much bigger Kuiper Belt object than any others. That would still be an interesting find, whether or not it meets the planet criterion.
Absolutely,
Something 10 times the mass of Pluto in the middle to outer part of the Kuiper Belt would be a good find. But I'm told it's not. It's worth looking into, but don't hold your hopes up.
There's many really fascinating objects in the far Kuiper Belt. One in particular, and I'm going to butcher the name, Huaima, is a really unusual object. Yes, because it's sort of twice as long as it is wide. So it's a really weird oblate spheroid, and it rotates quite fast, I think. And it's thought to be the product of a large collision in the Kuiper Belt and then reaccretion of material. And so that's billed as one of the most exciting Kuiper Belt objects.
And spinning too fast to assume a spheroidal shape.
Yeah.
Okay, we've gone on too long. I think we have.
We will wrap up now. Yes, but it was a
pleasure
to answer your questions. So thank you for sending them in.
Thank you for joining in, everybody. There is another Planets and Moons chat on Wednesday, the 2nd of March, and we'll have the Moons Moot running by then. I don't know who my guest will be then. I'll probably find a Moony person, so you're off the hook. but thank you, Martin, for joining me.
It was a pleasure.
Been a pleasure. And Kate and Ben in the back room, thank you for running things so well. And thank you, everybody, for the questions. This will be on replay soon and on YouTube within a day or two, I hope. So live long and prosper, everybody.
Thanks for joining us. Cheers.